recording. Okay.
I took care of it.
Okay. Yeah, I started it now.
Okay.
Okay. So when I said non-equivalent hydrogens, what did I mean? Can anyone like either unmute yourself or just type it in the chat?
Does that mean the environment of the molecule is not the same as the one that's in this neighboring hydrogen? For example, if the bond is not rotate and they have closer to one of the oxygen or other electron group, then the electron density environment will be different from others.
Yeah, exactly. So you're right. I was talking about hydrogens that are not in the same chemical environment and are separated by each other by a single bond that allows for free rotation. So let's take a look at the structure on the left. These hydrogens on the methyl group in purple are attached to the same carbon, so they are equivalent hydrogens, and we'll think of them as one group. So the group next to it is the CH2 group, which is in a different environment because one, it has less hydrogens, and two, it is attached to an alcohol. The hydrogen in the alcohol is also in a different environment because it's attached to an oxygen. So this molecule also has no symmetry. So all of the groups are in different environments. Molecules that are symmetrical have more than one group of hydrogens that are in the same environment. So looking at this benzene ring to the right, you can see the blue line of symmetry. So this group of 3 hydrogens on the left that make up the methyl group is next to this hydrogen in pink and the alcohol in yellow. You can say the same thing about the hydrogens in the methyl group on the right. So they are next to the alcohol and this hydrogen. Since they are both next to the exact same things, they are considered to be in the same environment. The same thing applies to the hydrogen in the alcohol group. So both of these groups are in the same environment because they are both next to the methyl group and the hydrogen in green. So can anyone tell me why this hydrogen is different from this hydrogen, the one in green and the one in pink?
I'm gonna chime in here for a second. Think about it like when you think about non-equivalent hydrogens, think about it like you're physically standing at that hydrogen point and then looking at what you can see. So if you stand at the green hydrogen, you look to your left, look to your right, and then you see what's there. And then you stand at the pink hydrogen, you look to your left, look to your right, and you see something different or the same. That'll tell you whether there's a difference or not.
Yeah, so the green hydrogen has different neighbors than the hydrogen in pink because it's attached to these 2 OH groups in yellow, while the pink hydrogen is attached to the 2 methyl groups in purple. All right. So, all right. So the structure on the left will generate 3 signals because the hydrogens are in 3 different chemical environments. And the structure on the right will generate 4 signals because all 4 groups are in different chemical environments. So I have some more examples here. Could anyone tell me how many signals each structure generates and to also box the groups of hydrogens in different environments using the whiteboard feature? I don't know if, oh yeah, the annotate feature. Yeah, so let's go back to the previous slide. So the molecule on the left will generate 3 different signals in the spectrum because there are 3 different groups of hydrogens that are all in different chemical environments. So this one, the benzene ring on the right, will generate 4 signals because there are 4 groups of hydrogens that are all in different chemical environments. Does that make sense? Okay. All right. Would anyone like to volunteer for the first structure? Okay, Brian, why do you say that the first group has two different signals?
Because I assume the two of the hydrogen at the ending is different from the four hydrogen that's in the middle, and therefore there are only two different two different types of environment they will be experienced by others.
Okay, so I understand your reasoning, but this molecule has one signal because all of these hydrogens are in the same environment. So if you think about it, like these three hydrogens are all attached to one carbon, and this carbon is attached to a methyl group, which is exactly the same thing as this methyl group on the left. So because you have that symmetry here, you will have one chemical environment. So all of these guys are neighbors.
I see, because the middle the carbon bond is can rotate, and that's why they all have the same environment.
That and because they're both attached to the same functional group, which is just each other. Does that make sense? Okay. And what about the second structure? Yeah, so the second structure over here has four signals. The methyl group on the right is attached to this ketone. So it's in a different environment. This CH2 group in blue is in a separate environment because it's attached to the ketone and this CH2 group. And this purple CH2 group is in its own environment because it's attached to the methyl group in light blue and this darker blue CH2 group. Does that make sense to everyone? Okay. And what about the third structure? Yeah, so the third structure also has two signals. Does anyone want to explain why? You can use the annotate feature to like draw the boxes.
It's because two of the ending hydrogen is different from the one in the middle.
Yeah, so the third one does have two signals. So this structure is also symmetrical, meaning that if you split it in the middle after the second carbon, you would get the same thing on both sides. So yeah, you can see the hydrogens here in red are different than the ones in brown. That's exactly right. So these two methyl groups are in the same environment as each other because they are both attached to this CH2 group, and the CH2 groups are both attached to the methyl groups. Does that make sense? Mm-hmm. Okay, and what about the last structure? Yeah, so this structure is also symmetrical if you consider the third carbon to be the line of symmetry. So similar to the structure before, you have these two methyl groups that are attached. Let me box it. You have these two methyl groups that are attached to the brown CH2 groups, and both of these CH2 groups are bound to both a methyl group and the blue CH2 group here in the middle. So that would give you three signals. Does that make sense? Okay. All right, I have a question for you guys to do, and I'll give you about 2 minutes to complete it. All right, that was 2 minutes. So, all right, it looks like a lot of you guys got B, which is the correct answer. Again, if you're okay with me calling on you to explain your reasoning, just type like an asterisk in the chat. All right, Brian, why did you say B?
Because the one that's close to the left, the 3 hydrogen has all the same NMR signaling. And in the benzene, there are 2 different kinds. If you look horizontally, you will see there are 2 different group of hydrogen being experienced by the nearing electron group.
Yeah.
And then in the end, that's close to the double bond hydrogen. On the right, you have 2 different kinds of signaling. The one in the ending with the 3 hydrogen has same chemical group, and the 2 hydrogen next to the end has also the one under one group.
Yeah, that's exactly right. So, yeah, I like how you mentioned the line of symmetry. So in the benzene ring, we can see that an internal line of symmetry that Brian mentioned here in red. So these green hydrogens are the same as each other because they have the same neighbors, which would be this oxygen here. And these hydrogens in blue. So the hydrogens in this methyl group are in their own environment because the group is attached to this oxygen here. So if we look at the other side, the methyl group in purple is attached to the CH2 group. So each of these groups are also in their own environment. So counting all the different colors that we have, which represent the different environments, we can expect to see 5 signals in the NMR spectrum. Does that make sense? All right. Okay, so I have another question for you guys to do. Again, if you want me to call on you, just type like an asterisk.
Hey Ashley, just FYI, we got a question in the chat from Josie that's I think referring to a specific question regarding the benzene.
Oh, I just saw it. Okay. You consider resonance. Hold on.
Yeah, so I guess I'm wondering why it counts as 2 separate environments when it's, but I guess I saw what Brian said about there's no rotation. So I always assumed that there was rotation in a benzene ring. And so I thought it would really.
Ashley, would you mind going back to whichever one was related to the benzene ring? I don't remember which one that was.
Well, I don't think it's a benzene ring. It's just like even this one has an example of it with the ring structure, the cyclohex. Yeah, the cyclohexane there. So I guess it counts as 2 separate environments, but normally wouldn't there be rotation?
Well, I mean, the ring is, so rotation where is the question I would ask you.
Oh, I guess
Because if you
like
look at it,
within,
like if you're sitting on the on either of the blue hydrogens, you'll see a carbonyl group right next to you, and then that methoxy group farther away from you. Whereas the green ones, you'll see the methoxy group right next to you, and the carbonyl group farther away. So those are two different environments.
okay, I think, yeah, that makes sense. I guess I was looking at it as I was confusing two concepts maybe with resonance and the actual structures.
Yeah, so I wouldn't. So resonance doesn't matter a ton when it comes to this stuff. At least with like with this particular example with the benzene ring, because essentially all the bonds in benzene are equivalent. So it's not like one resonance structure is going to be better than another resonance structure.
Okay, thank you.
Yep.
All right, it looks like I forgot to set my timer for 2 minutes. So let's just go over the answer for the other question. So, GOT, did you want to explain how you got C?
Yeah, so I guess it's just looking at the environment. So the methyl group on the end, and then each of those groups are different environments. And then, yeah, that plane of, I had initially thought that the structures attached to the ring counted as separate ones,
Yeah.
but now I see that there's a plane of symmetry, so it would count, it would be half what I had originally thought.
Yeah, exactly. So, yeah, unlike the previous structure, this molecule is entirely symmetrical, so we can expect to see fewer signals. So starting with our line of symmetry in red, we can see that these hydrogens in purple are all in the same environment because they are all neighboring a hydrogen and this ketone here. The CH2 group in yellow is neighboring the ketone group and the methyl group in orange. If you look at the CH2 group on the other side of the structure here, you can see that it is attached to the exact same thing. So they are both in the same environment. And the same goes for the methyl group in orange. All right. So a formula that can be very useful and that you do need to have memorized is the one to find the degrees of unsaturation. So the degrees of unsaturation a molecule has can be found by multiplying the number of carbons by 2, adding the number of nitrogens and subtracting the number of hydrogens or halogens. And finally, dividing this number by 2. If you get 0 degrees of unsaturation, then you have no double bonds and there is no possibility that this structure can be a ring. If a molecule has 1 degree of unsaturation, it can either have 1 double bond or it can be a ring. If it has 2 degrees of unsaturation, then it can either have 2 double bonds or a ring and a double bond and so forth. This chart makes it easier to visualize. Does that make sense? Okay. So let's do an example together. So C5H10 has an H1 NMR spectrum with only 1 peak. So can anyone tell me how many degrees of unsaturation this molecule has and what the possibilities are in terms of the number of double bonds or if it's a ring? You can just type your answer in the chat. Yeah, exactly. So the molecule in question has 1 degree of unsaturation, meaning that it could either have a double bond or it could be a ring. But in the question stem, we're only told that it only has 1 peak, meaning that there's 1 group of hydrogens that all share the same environment. Therefore, do you think that the structure would be a ring or would it have a double bond? Yeah, exactly. So the structure would most likely be a ring. All right. So the structure is a pentane. You can see that all of these groups of hydrogens are all in the same environment. They have 0 non-equivalent hydrogen neighbors. If we look at the double bond structure on the bottom, we can see that there are at least 3 different groups of hydrogens that are all in different environments. So we would see 3 signals and not 1. All right. Does anyone have any questions about this? Does it make sense? All right. So, like I said before, the splitting pattern can tell you how many hydrogens are interacting with each other. So let's look at 1-iodopropane. We can see that there are 3 different hydrogen groups here in blue, green, and red. So we can expect to see 3 signals. In each of these 3 signals, we can expect to see different peaks. So let's start with the methyl group in blue. These hydrogen atoms have 2 non-equivalent hydrogen neighbors in green. So the peak representing the methyl group will have 3 signals. This is where we start using the N+1 rule, which we'll talk about more in the next slide. The CH2 group in green has 5 non-equivalent hydrogen neighbors in blue and red, so it'll have 6 peaks. Finally, the CH2 group in red has 2 neighboring non-equivalent hydrogens in green, so it'll have 3 peaks again. Does that make sense? Okay, hope it does. So the N+1 rule is used to determine how many non-equivalent hydrogen neighbors a group of hydrogen has, like we just did. So the letter N represents the number of neighboring non-equivalent hydrogens that are 3 sigma bonds apart, which you add 1 to in order to get the splitting pattern. So if you see a singlet, that means there are no neighboring hydrogens. If you see a doublet, so like 2 peaks, then you have 1 neighboring non-equivalent hydrogen and so forth. All right, does that make sense? Are we ready to do an example together? Okay. So, for example, ethanol has 3 groups of hydrogens in different environments. So we can see 3 different peaks here in the spectrum. So can anyone tell me which groups of hydrogens correspond to peaks A, B, and C? You could say like blue is to B, A is to green, red is to C. I don't know. Yeah, Brian, that's exactly right. So the methyl group has 2 non-neighboring hydrogens in green, so it'll be represented by this triplet that's labeled C. Remember the N+1 rule. The CH2 group in green has these 3 neighbors in blue, so it'll split into 4 peaks or a quartet. So it'll correspond to peak A. And the hydrogen in red in the alcohol group has no neighboring hydrogens because it is attached to an oxygen, which shields it from its neighbors. So it'll be represented by this singlet labeled B. Okay. So if we're all good with the n+1 rule, we will move on to the chemical shift. Oh, never mind. This is need to just like.
Yeah, okay, so this is something that I wanted to bring attention to. And we kind of went over it a little bit, which was how when you have a benzene, you have two substituents that are para to each other or on directly opposite sides. You actually end up seeing two doublets in this situation. So there's going to be two signals, each of them is a doublet, and that can be kind of deceptive initially because what's happening is you have two identical protons labeled A1 and A2, which are technically like they're not on the same carbon, but they have the same exact environment. So they're actually members of the same signal. And A1 is being split by B1, and A2 is being split by B2 in the exact same way, which results in the signals from two different hydrogens, both of which are doublets, being combined into one signal. And the same thing happens as B1 splits A1 and B2 splits A2. I don't know why. It looks like part of my written caption got cut off, but does that make sense? Essentially, what you're seeing is splits that are happening in different parts of the molecule, but because they're happening in the exact same way, two identical hydrogens are resulting in those signals coming together. So there's only two distinct signals for hydrogens on the directly bonded to the benzene pair. Does that make sense? Understood. Okay. So we're on the same page that there's two types of protons on the benzene ring, right? There's A and there's B. So there's only two signals coming from there. Okay. So A1 is splitting. So let's look at just the green, which is the A proton. So A1 is a doublet because it's being split by B1. And A2 is also a doublet, it's being split by B2, right? Okay, but because A1 and A2 are identical, and they're being split in the exact same way, since B1 and B2 are also identical, that A signal will be two protons, and it will be a doublet. Does that make sense? Okay, and then the same thing is true for B with respect to A. So the B protons will also be two hydrogens and a doublet. I'm just ignoring the H. I'm just ignoring the H in the NH2 and the OH. So there are two signals, but normally you'd expect only protons that are like normally in a lot of NMRs you have only protons that are attached to the same carbon or the same other atom will share a signal. But here the A protons, even though they're on opposite sides of the hydrogen or of the benzene ring, that the A protons are one signal and the B protons are another signal, but they're each doublets.
Does anyone have any more questions about this before we move on to chemical shift? Okay.
It's okay. It's okay if I can repeat again what he said and see if I got it correctly. See if I got it right. So basically, the A will have the same A will under the same signal, and all the B will under the same signal. And the one in the A when you counting the splitting, A can also also include the one in the B. So there will be, if there will be 2H, because there are 2H in the A, and this for the splitting, I mean for the peak there will be 2 peak, since there are only one H next to it. If you look at it
exactly.
individually. Okay.
Yeah. So you'll see if you're just looking at the benzene protons, you will see 2 doublets.
Sorry, so you'll see 2 doublets as opposed to what? Like
as opposed to what some people get mixed up on is that they think that because A, so like normally when you're looking at like adjacent protons splitting each other, what some people do is they don't realize that because A1 and A2 are being split in the exact same way, that those signals that it's only a doublet, and it's not like, you don't count the B1 and B2 protons separately because they're equivalent. When you're looking, you're not saying you're being split by two different protons. You're being split by the same proton twice. So, for example, some people might think that the A is a triplet because it's being split by B1 and B2, but it's not, because A1 is being split by B1 and A2 is being split by B2. So you're only really being split by one proton. Yeah, it's kind of a subtle point, but it's easy to mess up in certain situations.
So is that seems right? Like it's 2 signal, but the 2 doublet.
Yeah.
Okay.
I have a question. Do you mind go back to the previous slide? How do you calculate the saturation? Is it the O? The next one, please.
This slide?
Yeah, so I got the equation. So can you go back to the one with OH group? Just the one.
Wait.
No,
what's
the
after this?
after that.
Oh, this?
Yeah, this. So how do you calculate that?
So you don't calculate the degrees of unsaturation here because it wasn't asked of you to. Like, usually you would have to calculate degrees of unsaturation when a question gives you a molecular formula and you're trying to find out, like you're just trying to find a clue that would give you, that would help you like identify a structure. This example I was just using to show you like like how many peaks you would expect. Or like in how many, and how it would split. Oh yeah, like if you were to calculate the degrees of unsaturation for ethanol, it would be 0 because there's like no double bond and no ring because it's 2 carbons.
So hydrogen doesn't count at all.
Doesn't count in the degrees of unsaturation, or like what do you mean?
I think the H does not affect the number of the H that you could have in comparison to this for this state. Whereas if you're adding a nitrogen, you will basically adding one extra proton in comparison to the carbon skeleton original state. So which means in simpler word, if you erase the O in this case, the number of hydrogen is still the same.
Yeah. Yeah, wait, I don't think I was understanding the question right. Did Brian help you out or?
Yeah,
Um,
kind of. So
I think
yeah, so kind of the equation. So hydrogen just doesn't fill in the equation, right? We don't care about hydrogen.
Well, the number of hydrogens is important when you're calculating the degrees of unsaturation. So like we saw in the formula, it's 2C plus 2 carbons, like you multiply the number of carbons by 2 plus 2, and then you subtract the number of hydrogens always, and then divide that number by 2. Okay. All right. So chemical shift, it basically just tells you the location of the peak on the spectrum. So the magnetic field created by electrons in the neighboring functional groups can shield the nucleus. So the more shielding there is, the more upfield or to the right the structure will appear. The less a proton is shielded, in other words, the farther away it is from the electron cloud, the more downfield the proton group will appear, so towards the left. So I drew some functional groups here. These are just some examples of where you would find these functional groups in the NMR spectrum. So like carboxylic acids, aldehydes, amines, and phenols are all electronegative and de-shield the protons, whereas alkynes, alcohols, ketones, methyls, and halogens are all groups that cause shielding due to their electron cloud. So you don't have to memorize this diagram. It would just be helpful to know. I know I got a question about this on UWorld and I don't know, it just stuck with me. Okay. So here are some examples of the effect of electronegativity on a structure's chemical shift. So starting with ethane here, we only have 2 methyl groups attached to each other. So there's not, there is shielding going on, so we can expect it to be upfield, close to the 0 parts per million value. Next, we have chloromethane. So chlorine is very electronegative, so it's going to de-shield the hydrogens from the electron cloud. So that's why it's located more downfield. Does that make sense? Okay, because I have a question for you guys. So I'll give you about 2 minutes to do this. Type your answers in the chat when you're done. Again, I'll call on you if you put an asterisk next to your answer, which I encourage you to do. All right, Brian, why did you get C?
because in this relative to the central carbon atom, there are 3 branches of methyl, and in each methyl there are 3 hydrogen, and they are all experiencing the same chemical group under 9H doublet. And the doublet is based on the N+1 rule, which is relative to the central hydrogen atom. And the central hydrogen atom is experienced in this signal, this experienced by the 9 of the hydrogen atoms surround the central atom.
Yeah, that's exactly right. So I drew the diagram of what isobutane looks like. It's basically just 3 methyl groups attached to a central carbon. The hydrogens on the 3 methyl groups, like Brian said, they're all in the same environment and have 1 non-equivalent hydrogen that's attached to the central carbon in green. So the spectrum will show you 2 peaks because there are 2 non-equivalent hydrogen groups, right? The one in purple and the one in green. So one peak will split into a doublet, meaning that this group has 1 non-equivalent neighbor, which is the hydrogen in green. This peak, the other peak will split into a multiplet. So the green hydrogen has 9 non-equivalent neighbors, which are all the hydrogens in purple. So the way you define a multiplet, I think it's, need to correct me if I'm wrong, is it after 4? Or no, I think it's after 5.
I think it's after 5 or 6. Multiplet is like, I know it goes into quintet. I think honestly, I think there might be a sextet, but I'm not sure.
I know there's a sextet, but I know for,
I think it's after that probably.
yeah, I mean a lot of textbooks define like quintet as a multiplet. Yeah.
Yeah, I think that's accurate.
All
At
right.
least not conventionally.
Yeah. So I have another question for you guys. I'll give you 2 minutes. All right, Brian, why do you say C?
Because in the methyl group in the end next to the double bond hydrogen there will be 3H, but it does not near any hydrogen, so there will be a singlet based on N+1 rule. In the benzene there are two kind of H signal. Since the benzene will not rotate, so you can draw a plane of symmetry slide through the middle. And there will be two H, and next to it there will be two W. And then the quintet, since the one in next to a triplet, the two H next to a triplet is experienced by the triplet and also the doublet. So 5 plus 1 will equal quintet. And the triplet only next to two hydrogens, so a plus 1 will be triplet.
Yeah, so you were right on all like 4 out of 5. So the blue hydrogen groups here, that will split into a quartet. So it's not affected by these two hydrogens here in orange because they're not 3 sigma bonds away, right? So 1 bond, 2 bond, 3 bond, 4 bond. So that's why we only consider these 3 hydrogens as their neighbors. But you are right that
I have a question, but when I thought when we see a double bond, we can like count the double bond across to it. Like we will basically just count as an extension. I'm not sure if I was right because I learned this a long time ago.
No, I don't think I've yeah. From what I was reading, I don't think I've like read about like an exception with the double bond. I just know that neighbors are always defined as 3 bonds away.
Okay. Thank you.
Yeah. So yeah, Darlene, a hydrogen is only counted as a neighbor if it's 3 bonds away. And okay. Is the rationale for the doublets on the ring what Nitij was explaining? Nitij, do you want to chime in?
Oh, the rationale on the double. Oh, I didn't see that. Sorry. Yeah. So essentially, what's happening is, so the orange H is being split by the gray H, right? And then on the other side, another orange H is being split by another gray H. And essentially, what's happening is that's generating the exact same signal with the exact same split. And so it's kind of like the same signal with the same split twice, which then creates a 2H or 2 hydrogen signal that represents the orange hydrogen. Does that make sense? Okay, good.
All right, so I have a really short passage for us to do together. It's only 4 questions long, and after that, we'll be covering like one more thing and then we're finished. So I'll let you guys read the passage and the question. Let me know when you're done. Let me know that you're done by putting your answer in for question 1. All right, do you want to explain how you got A? I don't know if you meant to put like an asterisk or.
That's okay. So our ester has one double bond with hydrogen, another single bond with hydrogen, so it's not A.
Yeah, so the ester group, let me draw it out. I forgot to draw it out here. So the ester group, the answer is A, you're correct. But the molecular formula only contains one oxygen, so there's no way that it can be an ester since esters have two oxygens, right? So it would look like, oh my God, this is so bad. I'm so sorry. That would be an ester. So you see these two oxygens, these two oxygens make it impossible. Like there's no way that the compound X could have an ester. Does that make sense? Okay. All right. What about question 2? I'll give you guys like a minute to do this. You can type your answer in the chat. Okay, Brian, how did you get D?
Actually, I want to change my answer. I think there might be C, because alcohol and ester both have oxygen, which is very dense with electron polling, and whereas the carbon to carbon double bond is more like in the middle. It's the only one that does not have oxygen in them, which will causing the shielding or deshielding effect.
Okay, so wait a minute. I like made this question. I tried modifying this question, and forgive me, but I made a mistake. So I changed ketone to aldehyde. I wanted you guys to remember this diagram and like the effect of electronegativity on chemical shift. So you would be right if it was an sorry, I don't know if you said if it was a carbon-carbon double bond or an alcohol, but I wanted you guys to pay attention to the chemical shift value, which was 7.25 ppm, which means that it's very downfield. And functional groups that cause deshielding are carboxylic acids, aldehydes, and amines, and the phenols. So, and the functional groups that cause shielding are like alcohols, esters, the carbon-carbon double bond. So yeah, I wanted you guys to recognize that out of the possible answer choices, ester, which can be eliminated because we already eliminated that. But D and aldehyde would be our next best choice because it causes deshielding. So, do you guys have any questions about that?
I thought aldehyde would be like a pretty, although it's not as much as the carboxylic acid. I think aldehyde is also very close to the downfield, which is I think is close to 9, 10
Yeah.
or 9.
Yeah, so the aldehyde causes deshielding. So that like you could expect 7.25. That's like a pretty I guess high number for it to be considered like very deshielded. Does that make sense? Okay. So here's another question. Just type your answer in the chat when you're done. Okay, why do you say A?
Because A is, I'm just looking at the signal. A is the only one that says multiple. So it had to be the greatest.
Yeah, exactly. So you were using the n+1 rule. Yeah. So I have another question for you guys. This is the last question. Yeah, okay, I can go over this one with you guys. So if we treat the molecule with NABH4 followed by acidic workup, we would get an alcohol. So this new compound now has two new proton resonances, one for the hydrogen in the alcohol group and one that is now attached to the CH, to the carbon. That's also attached to the alcohol group. Does that make sense? Yeah, so true. Well, you could use the question 2 was the one that I modified, and that was the one that was hinting towards like a ketone group. So you would use the IR spectrum. So an important value that you have to have memorized is 1705 centimeters to the -1. So this tells you that there's a ketone group. And using this value, you would, yeah, so using this as a hint that the structure contains a ketone group, you would pay attention to that. And then once you like treat it with the NABH4 and the acid workup, it would be converted to the alcohol group. So another thing that you need to study is like reagents and the starting material and then the products. So NABH4 is like an excellent reducing agent. It's great at making alcohols. Does that make sense? Okay.
I have a question.
Yeah.
For the IR, you have two value. How do you know which? I think the first value is very close to the just alcohol group. How
Yeah.
do you know you are not using the first one but using the second one instead?
Well, you can't really reduce an alcohol group more because the oxygen is already attached to the hydrogen. So the next one that you would pay attention to would be the 1705, which tells you that it's a ketone group. So the ketone group is readily, it can be, it can be reduced easily, a lot more easily than the alcohol group.
Wow, that makes sense. Thank you.
Yeah. You would be hydrating the ketone.
Mhm.
All right, and that was my portion of the PowerPoint, but I will go over integration with you. It's very simple. I don't think this would come up. Like this feature isn't really focused on that much in the MCAT. So basically for integration, it just tells you how many, a relative number of hydrogens in a signal. So like Nitij pointed out, it's always proportional, it's not exact. So you would just pay attention to the, I guess, height of the peak and compare them to each other. So this one has like a 2-to-3 ratio. So A would have 2 hydrogens and then B would have 3 hydrogens. And this one, the height of this peak over here, this tells you that it would be like a 1-to-6 ratio. And you can see that in the structure that A has like 6 hydrogens and B only has 1 hydrogen. Again, it's not really like a high yield topic. It's just something that can help you. Does that make sense? Okay. All right, and this was another note about proportions. So I can have Nitij go over this when he is available next. He had to leave the meeting for a bit, but yeah, I'll have him go over that in the recording, and then we'll upload it to YouTube. So this was also another note about carbon NMR. Again, Nitij will go over that. So thank you guys for coming to today's topic session and for participating. I hope that what we covered today helps a little bit. So I will be sending out an email with the slides and some more information. So keep an eye out for that. And we hope to see you in future sessions. I'll go talk to Nitij about the last 3 slides as well. And if you have any more questions, I'll be sticking around for a bit. Of course.
I have a question, but it's not relating to the today's topic.
Yeah, what's up?
I just want to know from different opinion, how do you usually